Dear students, in this module, I am going to introduce you to scoring matrices. As you already know that pairwise sequence alignment or comparison of two sequences as a pair is essentially to compare their constitution. The constitution can be from amino acids or nucleotides. So when you want to compare these two sequences, then you want to score the result. But in the real life, due to the evolutionary pressures, the rate of replacement of different amino acids by others is different. So therefore, it is necessary to incorporate this variable propensity of replacement or substitution by suitable scores. In this goal, we are helped by scoring matrices. So we will see what are the scoring matrices, how do we build these scoring matrices, and how we can use them in the alignment problem. So as I just mentioned that the amino acids, for example, can be replaced by other amino acids based on their chemical and physical as well as spatial properties. So if two amino acids are similar in their chemical behavior, then there is a high chance that they will be substituted during evolution. However, if they have starkly different properties, then there is a very low chance that such an amino acid will be replaced by a very different amino acid. So the scoring matrices, they are variable or flexible in scoring such substitutions, and therefore they have the substitution for each amino acid scored differently. Let me repeat that scoring matrices have the substitution scores for each amino acid in a unique way. So how do we build these scoring matrices? I will show you an example of the scoring matrix in a minute, but the first thing that we need to understand before looking at such matrices is that how do we build them? So what we do is we look at the protein sequences that are there in nature, and we find out those protein sequences that are similar to each other or homologous to each other. So once we have isolated a set of similar protein sequences, then we see which amino acid in one sequence is substituted by which other amino acid in the other sequences. In this way, we build a frequency list of amino acids. That is, how frequently an amino acid is substituted by which other amino acid. So the scoring matrix, by looking at such frequencies, may contain a positive number, that is, a very easy transition or substitution from one amino acid to another, a negative score, which means a very rare substitution, or maybe a 0 as well. So here is an example in which we have taken a protein called ubiquitin, and we have listed several of these ubiquitins here for you, from humans, from chimps, from orangutans, and so on and so forth. And their sequences have been aligned with each other. As you can see, some of the amino acids are rarely substituted, while some others are completely conserved, while some other amino acids are changed or substituted like that. So what we do with such a statistics or frequency count is that we apply this formula that is given here. So this S will be your scoring matrix, and A will be the first amino acid and B will be the second amino acid. So substitution of A by B will be scored by multiplying some constant that we will discuss later by the log of this ratio. So what is PAB? So PAB is the probability of amino acid A being substituted by B in this entire data set. So A or B can be any two amino acids. Similarly, FA and FB, that is here, is simply the frequencies of A and B in the entire data set. So by computing S for AB, and if you vary A and B to be all the amino acids, that is 20 amino acids, you can arrive at the scoring matrix. I will show you the scoring matrix here. So this is one of the scoring matrices that we will discuss later as well. But just to briefly indicate some important things from this matrix. So here you can see we have negative scores, that is -5 when D is substituted by W, or zeros if S is substituted by D, Q, and G. Also on the diagonal, as indicated by this red line, you can see that the scores are very high, especially here if C is substituted by another C. So the score is substituted by 13, which means that C is mostly conserved. C is most probably converted into a C and it will be scored with a 13. And of course you can also see other amino acids substitutions which are scored negatively. So in conclusion, as opposed to our earlier approaches where we assigned a match a +1 or a +5 for all the matches, or similarly -10 or -2 for mismatches for all the amino acids, the scoring matrices selectively score and score differently for each amino acid depending on their chemical and physical properties which are reflected in their frequency of occurrence.